Let us now talk about linked list implementation of stack in Java. So we need to create our own MyStack class that supports these operations. This is an example usage of this class. We can create an instance. We can have push operation, which is going to push an item to the stack. One more push call here. Then we have peek operation. Peek operation simply gives you the top of the stack. So you get 30 in this example. Pop operation gives you the top of the stack and also removes the top of the stack. So you are going to get 30 and stack is going to modify like this. Push operation here again going to add an item 40. Size operation is going to give you how many elements are there in the stack. So you are going to get 3 here. IsEmpty returns a boolean value. It returns true when the stack is empty, otherwise it returns false. In this case stack is not empty, so we are going to get the false. We need to implement all these operations in MyStack class and we need to use linked list to implement these operations. And time complexities of all the operations should be big O of 1. Now please pause this video and try to write down a linked list implementation of stack that has all these operations in big O of 1 time. Let us now get an idea how are we going to implement all these operations using linked list in constant time. So this is how a stack works. In a stack, you need to do insertions and deletions at one end only. We have discussed this earlier. It's like a box which is closed from the one side. So you need to pick an end. You can either pick head or you can pick tail. Let's first talk about tail implementation. So if you always do insertions and deletions from the tail, and if you have only head reference, then both insertions and deletions are going to become linear time operations, which is costly. We want constant here. Even if you maintain tail reference, the insert operation would become big O of 1. With tail reference, you will insert after the tail and you will update the tail. But delete operation will still be linear because you will have to find the second last node to delete the last node, right? Because next of this has to be changed. So the only way to implement from the tail is to have a doubly linked list, because when you have a doubly linked list, you can delete the tail with tail reference and you can insert at the tail also. Why to do all that extra work when we have head operations, insert and delete both in big O of 1 time? So with head operations, whether it is a singly linked list or doubly linked list, you can always do insertions and deletions both in big O of 1 time. So we are going to use a singly linked list with only head reference. And to push an item, we are going to push it at the head, and to pop an item, we are going to pop from the head. When you want to push an item, you simply need to create a new node, right? And you need to make new nodes next equal to current head and head equal to new node, that's all. When you want to pop an item, you simply need to change head to head next. It's as simple as that, and all these are constant operations. Now how to make size a constant operation? See, if I traverse the linked list every time to know the size, I will have to take linear time. So to make size operation in big O of 1 time, with head reference, we maintain one more size variable. We increment size in push, we decrement size in pop. And we want to know the size, we can simply return the size variable. So that way we can implement size also in big O of 1 time. IsEmpty can be done easily in big O of 1 time. You need to check whether head is null or not. And you also have size. So you can also check size is 0 or not. So please pause this video now. You have the whole idea. Please implement MyStack class using linked list node. Here is complete linked list implementation in Java. So we have the same node class that we had in linked list, right? Because we need to use linked list implementation. So we have the node class which has data and next, and we have a constructor inside it which initializes the data with given value and initializes the next as null. Now we are going to use this node class to create a linked list. And this is where we have our MyStack class. Inside this MyStack, we have head reference for the linked list. We also have size as 0. Inside the constructor, we initialize head as null and size as 0, right? Which is obvious because linked list is empty. Empty linked list means head null and size is 0. Now, size function implementation, simply return the size. IsEmpty function implementation, return whatever this expression returns. If head is null, then return true. If not null, then return false. Now, push implementation. Let's understand push with these examples. Initially head is null, you want to insert 10. So what you will do, you will create a new node, right? And you will have a reference of this in a variable temp, right? And after that, you will make temp.next equal to head. So temp.next is going to become null. Head was null earlier. And then you will make head equal to temp. So head now becomes this temp node. And this is what you want, right? After that, if you do one more push, so this will be your temp initially, then you will make temp.next equal to head, so this will be linked, and then you will make this as head, right? So this becomes your new head. So this is how push function works. It handles both null and non-null cases. It also increments size. Size is also incremented by this function. Now pop function has to handle underflow. If somebody tries to pop an item and if linked list is empty or stack is empty, then we should do something. To handle underflow, we are returning a special value here, integer.max value. So user of this class can check if pop function is returned integer.max value, it means the stack is empty and I'm calling the pop on it. And user, by putting an if condition, can determine whether the linked list was empty or not. You can put an error message also inside this if condition, right, to handle empty stack. So this is corner case part. After that, say we want to pop this item 30 from the stack, what you will do? You will first store this 30 in a variable, right? You will get head.data, and then you will change head to head next, right? And you will do size minus minus. That's all we have done. We have stored head data in result variable, changed head to head next, did size minus minus, and returned whatever we stored earlier. So this is all pop function does. Now peek function again has to handle underflow. If somebody tries to call peek on an empty stack, then this should return a special value to indicate that the stack is empty. You can throw an exception also in both these cases, here in the corner case here and here, right? Exception throwing is also an option. That's what standard stack class does. Now peek function here in our implementation, my implementation here, I'm returning integer.max value as a special value. And after handling the corner case, peek simply means get me the top of the stack, and top of the stack is head here because we are inserting and removing from the head. So I'm simply returning head.data. So this is peek implementation. If I call peek on this stack, I'll get 20. If I call peek on this stack, I'll get 30. Now what are the time complexities of all these implementations? If you see all these implementations, we are not having any loop in them. We are simply doing some constant number of operations. So time complexity of every function here, every operation here is big O of 1. So this is linked list implementation, and we have big O of 1 in the worst case, right? If you see normal array implementation, there we had big O of 1 in the worst case, but the size was limited. Then we had array list implementation where we had big O of 1 amortized, where we were allowing dynamic size. Here we have dynamic size and we have big O of 1 in the worst case.